Welcome to Lab 3, Estimating the Mass of a Black Hole. For this lab, we are able to observe the motion of a star orbiting around a black hole. Our problem is to try and find the mass of the black hole from the motion that we can see. This is important because if the star is orbiting around something we cannot see with a certain mass, per the laws of physics, it provides evidence for the existence of black holes. In this lab, we'll first go through some assumptions that we need to make to solve the problem. Then we'll go through the fundamental physics that we use to solve it, and then using that information, we can use a computational model to visualize the components of the star's motion. And then we'll discuss if there's any potential improvements that we could have made. Finally, at the end, we'll go through some discussion questions. Our system in this problem is the visible star that is near a black hole. So can we calculate the F-net acting on the star? To do this, we need to make some assumptions and list some initial conditions. In this problem, we're given the mass of the orbiting star as 2 times 10 to the 30th kilograms, and the time between the data points is 1 day, which is this many seconds. We're also assuming that the location of the black hole is at the origin, and that there's only one force acting on the star, in this case, the gravitational force of the black hole that is pulling on the star. Now we're ready to solve for the unknowns using Newton's second law. According to Newton's second law, F-net is equal to the instantaneous change of momentum as a function of time. When you break up the components of dp/dt, it's equal to the change in magnitude of momentum plus the change in direction of momentum, both as a function of time. We can also write this as F-net parallel plus F-net perpendicular is equal to F-net. Now, since there's only one force acting on the system, F-net is equal to the force of gravity by the black hole on the star. And this also means that the magnitude of each will be equal. We know that the magnitude of gravitational force is equal to the gravitational constant times the mass of the star times the mass of the black hole all over the magnitude of the distance between the masses squared. And since we're solving for the mass of the black hole, we can get this equation here. Now, if we use the information we found in the previous section and plug it into GlowScript, we can make a model that will show us the parallel, perpendicular, and net force as the star orbits around the black hole. F-net parallel arrow is in magenta, the F-net perpendicular is in cyan, and the F-net is in orange. Most importantly, the computational model allows us to calculate the mass of the black hole, which is estimated to be 1.71 times 10 to the 34th kilograms. For more detail on the computational model I made using GlowScript, feel free to visit the link in the description below. So, was there any way we could have improved our prediction of the black hole's mass? One thing that comes to mind is time. When close to a black hole, since the mass of it's so big, it bends the space-time fabric quite significantly. To improve this prediction, we can use Einstein's theory of relativity. What does it mean? How is net force and its parallel and perpendicular components different from the rate of change of momentum and its parallel and perpendicular components? Well, mathematically, according to Newton's laws of physics, there is no difference in value between the two. However, in terms of what we can observe in this lab, to calculate F-net, we had to know the mass of the black hole, and to calculate the rate of change of momentum, we can use the observations of the position and the velocity of the system. Now, would we be able to tell the difference if we replace the black hole with a different one if the star's motion stayed the same? No, not with the physics that we use in this lab. For this lab, we use the observation of motion of the star to calculate the mass of the black hole using this equation. So if the motion of the star does not change, we assume that the mass must be the same as the previous black hole. Thank you for watching. Have a great day.